Here we have to rank acidities, and we've got a set of compounds that we have to do that for. And these kinds of problems often are difficult for students at this point because they've learned how to memorize acidities of things, but they don't really understand acidities of things, even though they were supposed to establish that from general chemistry, but they haven't had enough practice. So that's what this kind of question is about. If you're going to follow my advice, you're going to take each one of these, and if you're asked about acidity, we're going to turn that around and we're going to answer it on the basis of the basicities of the conjugate bases. Okay? Not on the basicities of these species, that's not relevant. It's the basicities of the conjugate bases. So we've got to turn each of these into its conjugate base. And you have to understand something about acidity and basicity in order to even make the best conjugate base. So let's do that. So here's the first one, and then the rest. And now we have a little bit simpler question. Now we just need to focus on the stability of the electron pair that in this case is associated with the negative charge. The first thing to notice is that the atom that bears the negative charge, or the atom with the lone pair in question. So here we've got an oxygen, oxygen, nitrogen, oxygen, oxygen. So the one that stands out is, of course, this nitrogen, and nitrogen is less electronegative than oxygen. So this negative charge is going to be less stable than any of the negative charges on any of the oxygens. That makes this species the most basic species. The most basic species is the conjugate base of the least acidic species. So here's our weakest acid. Considering the other four, I'm now on all oxygens. And you might notice that each of these conjugate bases can be stabilized by resonance. Let's draw one resonance structure, let's say for this one, that will be exemplary for each of these other species as well. So all three of these, being resonance stabilized, are more stable than this conjugate base. So this conjugate base is a stronger base than either of these. So this comes from the next weakest acid. So let's write that in. Now we need a way to differentiate between these three. And we'll notice, of course, that these two have fluorine in them, and this one does not. And so if we look at this, well, the fluorine is more electronegative than carbon, so there's a dipole on that bond between carbon and fluorine. We can draw that in to remind ourselves. That dipole causes an inductive effect that pulls electrons toward the fluorine. That stabilizes this negative charge. Both of these have that, and this does not. So this is not stabilized by what we call the inductive effect of the fluorine. So this is our next strongest base and comes therefore from the next weakest acid. So now we're left with this one and this one, and we'll see that this fluorine is further away from our negative charge than this fluorine. The inductive effect drops off with distance. That means that the inductive effect is greater here than it is here in terms of its stabilizing effect on the negative charge. So this is less stabilized by the inductive effect than this is. So this is our next strongest base, so it comes from the next weakest acid. So we have our order. So that's one strategy, and this is a relatively easy example. Another strategy would be to just take each pair. So I could have considered these two and said, all right, which one of those is a stronger base? Well, that came from the weakest acid. And then I could go to this, say, which one of those is a stronger base? Well, that came from the weaker acid. And then find out the orders for each one pairwise and then deconvolute that information. This is a good way